Welcome to the last video of the chemistry year. Well, not last video, but the last day of the chemistry year. I know, sad tear. I shall miss you all. But before I get along to missing you too much, let's get to some good stuff. All right, write the reaction for the ionization of acetic acid, and then write the equilibrium expression. I want you to pause. You should be able to do this quite quickly by now. Okay, so this is sort of a check for you. So pause. Meet me back here. Go. So the reaction for the ionization of acetic acid is HCH3COO plus H2O liquid yields H3O plus hydronium ion plus acetate ion, and I'm gonna stay consistent and write CH3COO minus. Notice I could also have written this C2H3O2 minus, okay? But I'm just gonna stay consistent and keep acetic acid like this the whole time, okay? Now the next step is to write the equilibrium expression. Well, you might have needed a little review here, but KEQ equals concentration of H3O plus times the concentration of CH3COO minus over concentration of HCH3COO. All right, so notice that if we have any acid in water, okay, this is always going to be the same, right? It's always going to be very similar to this. So if I say that my acid is just HA plus H2O, okay, plus H2O yields H3O plus the anion of the weak acid, A minus. All right, notice it's always going to look, this equilibrium expression is always going to look similar, right? H3O plus times the anion of your acid times the acid itself. All right, so this equilibrium expression is always going to be true. And because it is always going to be true, we give it a special K, which I guess at this point in the year is maybe not that special, since this is probably like the 15th K that we've had. But this one goes by the special moniker K sub A. If you can guess what sub A stands for, I'll give you a cookie. I won't actually give you a cookie because baking's not really my thing. But it stands for acid. This is the acid ionization constant. Acid ionization constant. All right, not a whole lot more to say there. You know how to solve these. I could also do KB, which would be for a base, all right? In which case, the equation for that would be not HB, because it's not going to give up a proton, it's going to accept a proton. I'll just start with B plus H2O yields OH minus plus HB plus. Notice that my charges balance out, as do my charges up here. Okay, so it's not going to be a whole lot of difference. The KB would be OH minus times HB plus over B, and that's really it. Okay. Now there is one other way of expressing the sort of strength of an acid. Remember, that's kind of what Ka would tell you, right? How much this acid, how successful this acid is at forcing its proton onto the donor, right? Like, so how much equilibrium favors either the products or the reactants, so how strong the acid is. So Ka is one way to do that. You could also do percent ionization, okay? And percent ionization is just like what it sounds like. It's a percent. It tells you the percent that your acid ionizes. So in the simplest terms, that would just be the concentration of HA that ionizes over the concentration of HA. That doesn't. So the initial times 100%. Okay, well, that's great and everything, and yay, I have an equation for percent ionization. But I'm going to argue that this is maybe not the best equation that we could come up with for this. Because if I look up here, any acid that ionizes forms H3O plus and A minus. Ah, that's what ionization is, right? And this H3O plus, we have a nice readout for using a pH meter. So I know that concentration of HA that ionizes is equal to concentration of H3O plus. Okay, I can rewrite this equation. Now, I also know that this would also be equal to the concentration of A minus, okay? But most of the time, you're not going to have an easy way to measure A minus, whereas you do have a way of measuring concentration of H3O plus. So, yeah, we can say this, but who really cares? So the better equation here is percent ionization equals concentration of H3O plus over concentration of HA initial times 100%. Okay? See if you can figure out what the analogous thing would be for a base. We'll use it at some point. Okay, so that brings us, that's basically the lesson for today. There are just a couple new things here, and then there are problems. And the problems, I'll admit, get a little gory, okay? So I'm just going to go through a few, and then I'll do some sample. It's just sample problems. That's what we'll do, okay? So here's our first sample problem. 3.7% of a 0.100 molar aqueous solution of lactic acid ionizes. The ionization of lactic acid is shown by the following equation. And then I've got this equation, and then from this information, determine the Ka of lactic acid. All right. Well, let's see what we got here. I know that I'm trying to find the Ka of lactic acid, which in this case is going to be H3O plus, times concentration of C3H5O3, which would be the lactate ion, okay? And then all of this over concentration of HC3H5O3. Okay, so this is what we're trying to find. So I'm given this 0.100 molar solution, okay? That's what I have. And then I'm also given that I have a percent ionization. All right, so let's look at our percent ionization equals, in this case, it's going to be concentration of H3O plus over concentration of the weak acid, HC3H5O3 times 100%. Okay, so I'm given this information, and I'm also given this bad boy, this 0.100 molar, is the concentration of lactic acid. So from that, I can find H3O plus, which gets me somewhere. Okay, so I guess that's a decent place to start. So remember to solve for your unknown. Okay, we're getting close to physics now, for those of you going on to physics, and this is an important skill to have. So concentration of H3O plus equals percent ionization times concentration of HC3H5O3 over 100%. Okay, I can plug some numbers in. 3.7% times 0.100 molar over 100%. And I get my concentration of H3O plus is 3.7 times 10 to the minus 3 molar. Okay, now at this point, I think it would be handy to kind of pull back a friend that we talked about briefly when we did equilibrium, and that is the Rice table. Okay, R-I-C-E. And no, that doesn't stand for rest, ice, compression, and elevation, which would be the appropriate steps to take if you sprain your ankle. These stand for reaction, initial, change, and end or equilibrium. Equilibrium. Okay, so I'm going to rewrite my reaction here. C3H5O3 plus H2O yields H3O plus C3H5O3 minus. All right, now our initial conditions, 0.100 molar. Well, what about our initial conditions of H3O plus and C3H5O3? I'll ask you again, what are our initial conditions of the products before the reaction has even started? You should come up with 0 molar, right? We don't have any products before the reaction started. The whole point of the reaction is to make products. So we have 0 molar for the products. And then what we're going to do is we know from here that our concentration of H3O plus is this. Now, where does that fit into this table? Well, this concentration of H3O plus we got from the fact that 3.7% of the solution ionizes. Well, if it ionizes, that means that it's formed the ions that we're talking about, right? Which means that this value, this 3.7 times 10 to the minus 3 molar, is really an equilibrium concentration. Okay, which means that my change, I went from 0 molar to plus 3.7 times 10 to the minus 3 molar. Okay? All right, well, this product, this H3O plus, is in a 1-to-1 mole ratio with this product, which means that this product should do the same. Yeah, all right. Now, what about this reactant though? Well, it is 1-to-1 with the H3O with the hydronium ion. So if the hydronium ion increases concentration by 3.7%, or 3.7 times 10 to the minus 3 molar, that means that this would have to decrease by 3.7 times 10 to the minus 3 molar, right? Because this is getting used up to create these. Okay, now some people get a little confused because I'm taking this much out of the reactant side and then I'm making this much of the products, right? Well, keep in mind, everything is in a 1-to-1 mole ratio. And the volume doesn't change. So if the mole ratios are the same, the concentration also has to be the same. Okay? You just got to keep that straight in your head. All right? Well, this is 0.100 molar minus 3.7 times 10 to the minus 3 molar. That's 9.63 times 10 to the minus 2 molar. Okay? And now I have equilibrium values. Okay, for H3O plus, C3H5O3 minus, and the lactic acid. Okay, notice that I don't really care about H2O because it's in such a huge excess that it's not really changing anywhere through here. All right, so these equilibrium conditions are really what I need to be plugging into my equilibrium expression, right? So I can just go ahead and do that. So both of these concentrations were 3.7 times 10 to the minus 3, so I can just do 3.7 times 10 to the minus 3 squared over the concentration of lactic acid at equilibrium, which is 9.63 times 10 to the minus 2, okay? And that's 1.4 times 10 to the minus 4. Now, how come only 2 sig figs? Well, this is an equilibrium constant, okay? Equilibrium constants, we said. If I'm going to ask you to calculate them, I'm only really want you to give me 2 sig figs, okay? Sometimes they'll give them to you with more sig figs, but when you calculate them, I just want you to use 2 sig figs, all right? And there's also no unit. Again, with an equilibrium constant, there are no units. Yay! Okay, so that's it. I mean, it's a long problem, okay? There are shorter ways to do this, but I really wanted to go through and I wanted to show you setting up the rice table. I wanted to show you thinking through everything stepwise, okay? So it does end up being a beast of a problem, but that's these problems for you, okay? So that's a good place to start.